Hello everyone, welcome back to my graph data structure series. So in previous three videos, we have explored the basic of graphs along with breadth first search, depth first search, and adjacency lists. Now, which works great for unvariate graphs or simple traversals. But what happens when we need to find the shortest path in variate graph where edges have different costs or distances? So today, we're going to dive into one of the most popular algorithms for solving this problem, Dijkstra's algorithm. This is used to find the shortest path from a starting node to all other nodes in a graph, and it works specifically for graphs with non-negative weights. So let's say imagine you're navigating through a city and you want to find the quickest route from one location to another location, but each road has a different travel time. That is essentially what the Dijkstra's algorithm does. We will
Okay, so
first
look, here
break
is my
down
graph.
how this
If you can see
algorithm
that
works
I
step
have
by step, and then
a
we will move
weighted
on to
graph here,
implement it
and
in our
along with the
code.
weighted, we also have a directions attached to this graph. So if you can see that I can go from A to C, and the distance between A to C is 3. I can go from C to B, and the distance between C to B is 6. I can go from A to B, and distance between A to B is 2. Similarly, we have distance for B to D. I think the distance between them is 1. B to E, we have a distance is equals to 4, and then C to E, we have a distance is equals to 2, and then D to E, we have distance is equals to 7. Okay, so this is our graph. So now what we have to do, we will have to find out the shortest path for each points, for each destination. So we have multiple points here, C, E, B, D. We have to find out the shortest path possible from the source A. So we are starting from source A. So let's say if I want to go to D, then I have to find out, okay, what is going to be the shortest path between A and D? So we have to implement that thing using the Dijkstra's algorithm. Um, so right now, I'm going to implement Dijkstra's algorithm using a priority queue. Okay, so I'm going to implement that using a priority queue. And I'm going to show you step by step how we can implement it. So first of all, we will have to understand how these things work. Okay, so first of all, so what are we going to need first? We are going to need adjacency list first. Okay, so we are going to need adjacency list first. So let's first of all create adjacency list. So for A, what is going to be my neighbors? So my neighbors are B and C. If you can see that, B and C, and what is the distance? And for C, we have 3. For B, who are my neighbors? My neighbors are D and E, and their distance from B is 1 and 4 respectively. So if I look from C, I have neighbors called B. They have the distance 6, and E, who has the distance 2. And then D, E, the neighbors of D are E. That's it. And then if I look at E, I don't have any edges. So we don't have to worry anything about E as of now because so as you can see that the E is a kind of a dead end because everybody's coming to E, but nobody's able to go back uh, from point E. So we don't have to worry about that as of now. Okay, so let me zoom out. Let me zoom this out a bit. Okay, perfect. So this is our adjacency list, and how are we going to create the queue now? So let's say this is our priority queue. We are going to implement it using minimum key. Okay, perfect. And also we will have to make sure we create a distance array because that is what we will be returning, right? That is what we are going to, that is what our main motto is, right? So let's go to distance array here. Uh, I'm going to name it as a distance, and that is going to be something like this. So A, B, C, D, and E. Okay, and each are going to represent the shortest distance one by one. Okay, so let's get this started. So this is looking of kind of fun. Now we will have to implement this. We'll have to put all of this together and we'll have to solve these questions. Now, now listen, we will start from A. Okay, so what is our main motto? Our main motto is to find the shortest distance possible, right? So first of all, we are here at A. So do we have any distance here, right? So no, so A is 0 because we don't have to go anywhere. We are already at A. So we don't really have to go anywhere here, right? We don't really have to go anywhere here. Okay, perfect. So now I have to go from A to B. Okay. So first of all, we will see what are the neighbors of A. So my neighbors are going to be B, and my neighbors are going to be A, B, and C. If you see that, my neighbors of A are B and C. And what is the distance here? So from A to B, the distance is going to be 2. And from A to C, the distance is going to be 3. Okay, perfect. So that is what we are going to store here as well in our heap. So in our heap, we are going to store uh, 2 comma B and 3 comma C. Okay. So as you can see that we already have the shortest distance defined so far. We are still exploring all the parts. We can maybe get some other distances as well. Okay, so now we are here at 2B and 3C. We have already it here in the store. So what do we have to pop here? So according to the min heap algorithm, we will have to pop the minimum, the most minimum, the smallest value we have. So we are here popping up 2 comma T. Okay, so we are popping 2 comma B here. Now, what do we have to do? We'll have to see, okay, who are the neighbors of B? So neighbors of B are here. We can easily have a look at the adjacency list. The neighbors of B are D and E. Okay, and already we have distance 2. So if I want to go to D, if I want to go to D, then my distance is going to be equal to 2 plus 1 is equal to 3, and I'll be at 3. I'll be at D with just distance 3. Okay, now the next question is I want to go to E. Okay, so now if you see that, what is the distance between E and B? The distance between E and B here is 4. So what are we going to do? We're just going to do 2 plus 4 is equal to 6. So now, so far, my uh, distance is 6. Okay, now, so we have to add these two nodes here as well. So I'm going to add 3 comma D, and I'm going to add 6 comma E in my queue. Now we have already popped this out, so we don't really have to go and look at the section B, right? So let me just erase that down. Okay, so we don't really have to look at the 2 comma B now because all the cases we have already explored. So now the next element which is going to pop is 3 comma D. So we are popping this out from our queue. Okay. So now I will have to look what is the, oh sorry, it's not 3 comma D, it's actually 3 comma C. Okay. So now we have to see what are the neighbors of C. So the neighbors of C is B and E. So from C here, you can go to D, or either you can go to E. So if I want to go to D, so let's say I want to go to C to D, my distance is going to be, we are already here at 3. Sorry, we already are here at 3, and it is going to be 3 plus 6 is equals to 9. Uh, but I already have a shortest distance 3 defined. So it is not going to match because it's obviously 9 is not lower than 3. right? So we are just going to ignore this. Now, let's say I want to go from C to E. Now, if I want to go to C to E, so what is the distance between C to E? It's just 2. So what is going to be the total distance? My total distance is going to be 2 is equals to 5. Now, if I compare that value from what I have in array, okay, yeah, so I have encountered my shortest distance. So we don't need 6 anymore, and we are just going to write it down here as 5. And similarly, we have 0, 2, 3, 3, 5. Okay, perfect. Now, what I can do is I will go here and erase this case as we are going to pop out the next elements that we have. Okay, so let me go back to this pencil. Okay, yeah. So now we are, what is happening, man? Okay, so now what is our next element that we want to pop out? We want to pop out 3 comma D. Okay, so we have 3 comma D case here. Now we have to see, okay, who are my neighbors? It's just E, right? And so let's say if I want to go to D to E, it's going to take me 3 plus 7, so 10. So it's going to take me 10 to just switch to E, but we already have a minimum distance defined here already, right? Because we already have a 5 here. So we don't need to go anywhere else. Now, we just have to go 6 comma E. And then if I see we don't have any edges, so we don't really have to worry about E in this case. So if I see what are going to be my minimum distances from point A to all of these points, so if I want to go to from A to B, I'll be able to reach A to B within just 2 distance, within the minimum distance 2. And if I want to reach C, it'll be 3. If I want to reach D, it will be 3 as well. And then if I want to go to E, so if I want to go from A to E, so rather than I go from A, B, from B, I'll go from C because it will be 1 point lesser than that. So it'll be just 5 instead of 6. So my minimum distance to reach E from A is going to be 5. So this is what the Dijkstra's algorithm is. Uh, I, I hope it made sense of how things work. We have to define priority queues. We have to define it in the way that it represents minimum heap. And then we'll have to keep track of all the uh, all the distances in our distance array. And we just have to return that distance array ultimately at the end. So this was the explanation part of the Dijkstra's algorithm. Now let's go into the code. We'll write the code in Java using priority queue, and then we'll see how these things work in code.
Okay, so now as we have understood how the Dijkstra's algorithm work, especially using priority queues, let's start implementing this in our Java code. It's going to be very simple. Uh, it has some of the it has some of the complexities involved inside the function, but that could be easily tackled, in my opinion. Okay, so let's get started. So first of all, before we start implementing a function, let's implement a class which is going to represent implement first a class which is going to uh, represent the pairs of node and distance. Okay, so let me start this static class pair. And inside that, we're going to have int node and int distance as our variables. And then we just need to create a constructor for that int node, int distance. And will be just this dot node is equals to node, and this dot distance is equals to distance. Yeah. All right. Now, so this was our class. Now let's start implementing our function now. Okay, so as we have discussed, we are going to need a distance array so that we can keep track of all our distances that are discovered so far. Okay, so we are going to need distances array, and that will be defined as dist. Okay, so now uh, if you remember, we just discussed that before we start to keep tracking of our distances of our all of our nodes, we'll have to make sure that at every index there is a maximum value, so that in the beginning we will have to initialize it with the maximum value. So integer dot max value. Okay. Okay. Now let's define the priority queue now. The vertex with the smallest distance is going to be at the top. We will implement this using a minimum heap. Okay. So priority queue pair PQ is equals to new priority queue, and inside that we're going to pass our size and pair comparator class. Okay, so pair comparator, what does pair comparator basically do? It will just return the node which has the smallest distance, because that's what we are looking for, right? So using pair comparator, it is going to prioritize the one that has the minimum distance. Okay, and we will have to define that as well. It'll be just a simple function which will return the minimum distance. So it'll be just like this. Okay, so it is just going to return the minimum distance, p1 distance minus p2 dot distance. Okay, perfect. Now we will have to initialize our source node, and also we know that the very first element sorry so very first element is going to be our source, and the distance will always be 0. So we are going to add it in our queue just like that, okay, at source s, at node s, my distance is going to be 0. Okay, so let's now start traversing the graph. Let's start processing the graph using priority queue. It is very similar to BFS, but now it is based on distance. Okay, so my while loop is going to be pq dot is empty. Okay, and then inside my while loop, what I'm going to do, first of all, I will have to define a current node. Okay, so I can define it using pair current is equals to pq dot pole. Now, let me explain you what pq dot pole actually means. So we all have used pq dot top for the majority of the times when we want to retrieve the topmost element from the queue, right? pq dot pole is going to do the same thing. Okay, it's not going to do anything different. But pq.pull is going to retrieve and remove the first element at the same time. And we need that, right? We need to pop the element as soon as as soon as we prioritize it, we'll have to remove that element as well, because we need to process it and then we'll have to go through the next nodes. So that's why we are using pq.pull. Okay, so now int u is equals to current dot node, int distance is equals to current dot distance. Perfect. Now we have to traverse all of our adjacent nodes to the current node, of the adjacent node to the current node. So whatever we have in our current nodes, we'll have to traverse through its adjacent nodes. Okay, I hope it makes sense. Array list, integer, and we are going to store it in a list called neighbor, and it is going to be adjacent dot get u. So in this way, we are going to get all the nodes that exist as a neighbor of the current node. So int v is equals to neighbor dot get 0. Okay, neighbor dot get 0, and this is going to be my adjacent vertex, and int weight is going to be neighbor get one, and that is going to be the weight of my adjacent vertex. Okay, perfect. Now relaxation steps is the shorter path to V is found, then we'll have to update the distance. Okay, so now we will have to go through all the distances, and if that distance is minimum, if that distance is lesser than what we have in actual, then we are just going to replace that distance and we are going to update it in our array. Okay, so that is going to be this. So if distance u plus weight greater than distance v, then distance v is equals to distance u plus v. Okay. And then pq dot add, we are going to add it in our queue. We're going to add a new pair inside our queue with a new distance. Okay. And then at the very end, I am just going to return distance. Okay. So that is everything for our code. I hope it works. Let's see. So it's getting compiled. It says it has a compilation error. I think I have messed up here in some of the syntaxes. Let me have a look. Okay, it looks like I have erased one of the braces here by mistake. That's why it was not working, and this should be there should be one more brace here, I guess. Let's see. Let's see if it is working. Okay, it still says it's not correct. Let me try this one now. Okay, so I have resolved the issues now with the braces. I just found out that I have made I have written one extra curly bracket, and that is why I was messing up the entire code. So now it seems to be working fine. If you can see that I've already compiled it, it says your output is 09, expected output is the same. That means it's working fine. So this was everything regarding the Dijkstra's algorithm using priority queues. Um, Also, there is a one more better way to implement this. Yeah, priority queue is very good and it is completely relevant and also very important to understand at the same time. But we also have a better way to do it. Interviewers can ask Interviewers can ask us to do it whether using priority queue or by using it by any other way. So we are going to see what that other way is in our next video. So until then, keep learning and keep coding. Thank you so much for watching.